Okay, so आज
फ्राइडे ना,
तो देवर सिंह की ये ओपन मतलब ये खाली है और मैं
फ्राइडे 9 to 10 क्लास है दूसरा सेक्शन के लिए.
नहीं बट बहुत आई रिक्वेस्टेड देम जो खाली हो वो करने के लिए. नहीं मैंने आई थिंक दीपा को बोला था कि बुक
कितनी शुरू हुआ था?
वैसे तो कुछ 100 के आपके लिए कितने
अभी कोर सेक्शन बी का सेक्शन ए है, पता नहीं
मेरे को
दीपा को
रिक्वेस्टेड व्हाटएवर सीसी में रखते हुए सबको
राजेंद्र को
मैंने
पता
बोला
होना
था कि
चाहिए.
ब्लॉक फ्री हो ना तो मैं देने के लिए बोला
राजेंद्र को पता होना चाहिए ना. IT 305 क्लास है फ्राइडे 9 o'clock.
अभी क्या कर रहे हैं आपका
दूसरा लेक्चर और खाली है.
वैसे LTG खाली ठीक है.
अब आप
जैसे तो मैं LTG में कर लेता लेकिन मेरे को शायद वो प्रिंट सॉफ्टवेयर का इंस्टॉल है ना लाइव वाला. ठीक है ना
वो लेक्चर और खाली है. खाली है.
ठीक. ये क्या रोग एनीवे सो okay, so I think we were looking at Cauchy residue theorem. I mean, yeah, we need to actually, I gave you the basic idea about it. So, last class we talked about Lorentz series and we talked about residues, and especially I think yeah, so we left at this formula of calculating the residues. Okay, so now let me show you some examples. So if you take example as f of z is equal to z divided by z minus 1 into z plus 1 whole square, then we know that z is equal to 1 is a simple pole, right? Means pole of order 1, okay, in this function. So residue I can compute. Residue at z is equal to 1 is limit z tends to 1 z minus 1 z divided by z minus 1 into z plus 1 whole square turns out to be 1 by 4, right? So this is a simple, I mean the formula that I told you, right? I have used this formula actually, right, to compute the residue. When order 1, actually when k is equal to 1, this will be, you know, there will be no differentiation needed. Just take the whole z minus a is z minus a times f of z and take the limit, right? Simple thing I have done. Similarly, if I want to compute residue at z equal to minus 1, so in that case limit z tends to minus 1 1 over factorial 1 d over dz. Now because you see z is equal to minus 1 is a pole of order 2, so k is equal to 2 here, right? So I can just compute d over dz z plus 1 whole square times z divided by z minus 1 into z plus 1 whole square, and this value turns out to be minus 1 by 4. You can compute. So by simple application of the formula you can compute the residue, okay, of a function, okay. So depending upon what kind of pole it is, I think even in the case of essential singularity we can find the residue. So let me show you how do you do that. Okay, so if z is equal to a is an essential singularity, then actually what you can do, just use Lorentz series expansion to find the coefficient a minus 1, which is the residue, right? So for example, if f of z is equal to e raised to power minus 1 by z, and we know that origin is here as an essential singularity, then e raised to power minus 1 by z is equal to 1 minus 1 by z plus 1 over factorial 2 z square minus 1 over factorial 3 z cube and so on. Therefore, coefficient of 1 by z, which is actually a minus 1, is what? Minus 1 here. Okay, coefficient here, this is minus 1, this is nothing but residue of f of z at z is equal to 0. So in case of essential singularity, I mean, you just expand it and find the coefficient, because residue is nothing but coefficient a minus 1 in the expansion, right? So if it is pole, I mean, you don't have to do the expansion, you can directly calculate because of that formula. Otherwise, you just expand it and look at the coefficient here. Here you see that minus 1 is the coefficient here. A minus 1 is minus 1, right? So that is the residue. Okay. Now I think I am going to mention actually the Cauchy residue theorem without proof, of course, and then I will show you a couple of applications so that how you can find integrations, and which is an important thing to do actually, right? Residue theorem, it's a pretty interesting thing. So suppose we have a f of z is a single valued and analytic function inside and on a simple closed curve C except at the singularities. Some finite number of singular points could be there, so maybe here, something like say A, B, C, right, and some more, right? Some finite number of singular points are there. Okay, at the singularity A, B, C, dot 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 inside C. Okay, and suppose the residues are given by A minus 1, B minus 1, C minus 1, and so on, right? So at each singular point, if I know the residue, which is A minus 1, B minus 1, C minus 1, etc., then the Cauchy residue theorem says that then integration along C f of z dz is 2 pi I sum of the residues. Okay, so this is 2 pi I A minus 1 plus B minus 1 plus C minus 1 dot dot dot. This is the Cauchy residue theorem. So clearly you can see that if there is no residue, this term will be 0, and actually you get the Cauchy theorem. So sort of a generalization of Cauchy theorem, is Cauchy residue theorem, right? So if the region has finite number of singular points, you just compute the residue at those points. Okay. So one way, if it is pole, use the formula that 1 over factorial k minus 1, right? Differentiate k minus 1 times all those things, f minus z minus a whole raised to power k times f of z, right? And take the limit. That is the thing if it is having pole. Otherwise, just use the Lorentz series expansion and find out the coefficient a minus 1. Okay, a minus 1 will be the residue of that function at that singular point, right? So this is the formula. So integration along C f of z dz is 2 pi I times sum of residues. Okay. Now let us see how useful this result is. It's very useful. First application that we are going to do is evolution definite integrals. The first one, minus infinity to plus infinity f of x dx, where fx is a rational function. Okay, I want to evaluate these kind of functions. F of x is a rational function. This is a real integration I want to do. Now I can use Cauchy residue theorem, and it becomes really easy to find out the value of this integral. Okay, so let us see how we do that. Okay, something very useful and very commonly used. Even in many exams they ask these questions. Pretty obvious. I mean, even in many competitive exams they ask. This is very common thing. Even say for example UPSC exam, IS exam, and everything. You know, this is something very nice. Okay, so let us see. So f of x is a rational function, means ratio of two functions, right? It's a rational function, and I want to find minus infinity to plus infinity f of x dx. Okay. So what I do, if I have to find this, I consider this kind of contour here. So first I will consider integration along C f of z dz along a contour which is something like this, from minus r to plus r. Okay. So this radius is r actually. This is a contour gamma. A semicircular region I consider. First of all, what I do? I generalize f of x to a function of a complex variable such that if I put y is equal to 0, I should get back to f of x. Number one thing, right? I consider a function which is a complex valued function correspondingly, right? So that when I put y is equal to 0, I will get the original rational function f of x, right? That is first thing. Second, then I am going to actually evaluate this integration along C f of z dz, where C is this semicircular region, right? From minus r to r. So this is a semicircle of radius r, and then this contour is there, right? So basically I am looking at this C here, right? Now so C is whole thing, gamma is this arc actually. Okay, this arc is gamma, and C is the whole simple from minus r to here and whole thing, right? I want to find this integral f of z dz along this C. Now what happens, since f of z is a rational function, so you know when denominator will be 0, those will be the singular points, right? At those singular points I see where if they are outside this region, then no problem, this integration will be 0 right away. If any of the singular point comes inside, I compute the residue at that point and then apply Cauchy residue theorem. The integration along C f of z dz is 2 pi I sum of residues, right? That's what we are going to do. Okay. Okay. So let us look at this. So this is a semicircle, right? Okay, so once we compute this, then we actually normally take limit r tends to infinity, so that it blows into the whole half complex plane, right? And r tends to infinity. Anyway, so let us look at this. And one more thing to note, if f of x is an even function, I mean, is it sufficient to evaluate 0 to infinity? Because those kind of things can be done. So let us look at example. 0 to infinity dx divided by x raised to power 6 plus 1. I have to find this value of this integral. So this is a rational function, right? So f of x is what? Can anyone tell me what will be the f of z? If I take z raised to power 6 plus 1, will it work? Because if I put y is equal to 0, z is equal to x plus iy, if I put y is equal to 0, I am going to get the same function, right? Okay. So this is our f of z. Okay. Now, so I consider this arc here, minus r to r, x axis, y axis, gamma. Gamma is this half semicircle thing, and we are considering the integration along c dz over z raised to power 6 plus 1. Okay. So this whole thing is c, right? C is whole thing, I mean not. So from minus r to r and the whole gamma, that is nothing but c, right? So what I need to do, denominator is z raised to power 6 plus 1. So z raised to power 6 plus 1 is 0, will imply that z is equal to e raised to power pi I by 6. I mean, you can solve it. Z is equal to e raised to power 3 pi I by 6. Z is equal to e raised to power 5 pi I by 6. Z is equal to e raised to power 7 pi I by 6. Z is equal to e raised to power 9 pi I by 6. And z is equal to e raised to power 11 pi I by 6. These are the values you can find, right? How will you find this? I mean, z raised to power 6 is equal to minus 1. So minus 1 you can write in terms of exponential, right? Okay. And then just solve it, right? I mean, minus 1 into e raised to power 2n pi you can add, right? Because e raised to 2n pi is 1, right? So then just do the calculations. So you get these 6 values of z. I mean, when z is for 6 plus 1 is equal to 0, you get these 6 values, right? Now the question is, which one will lie inside this semicircle? Okay. So that is what we need to find. And so basically these are all simple poles, right? These are all simple poles, right? Because the poles of order 1, because z raised to power 6 plus 1 is equal to z minus e raised to power pi I by 6 into z raised to power z minus e raised to power 3 pi I by 6 into z minus e raised to power 5 pi I by 6 into z minus e raised to power 7 pi I by 6 into z minus e raised to power 9 pi I by 6 into z minus e raised to power 11 pi I by 6, right? It's a product of all, right? So each of them is a pole of order 1. Okay. So I need to find which lie here. So I leave it for you to think why e raised to power pi I by 6, e raised to power 3 pi I by 6 and e raised to power 5 pi I by 6. Only these 3 lie within C. तो बाकी की हमको जरूरत ही नहीं, ओनली ये 3 खाली इस रीजन में लाई कर रहे हैं, राइट? सो दैट मीन्स जो बाहर जा रहा है अपर हाफ से, वो तो वैसे भी बाहर रहेगा, राइट? सो यू कैन एक्चुअली जस्ट कंप्यूट दिस. ओके. सो नाउ व्हाट आई नीड टू डू, आई जस्ट कंप्यूट रेसिड्यूज एट दीज 3 पॉइंट्स, राइट? Residues at these 3 points. So basically residue at e raised to power pi I by 6 is limit z tends to e raised to power pi I by 6 z minus e raised to power pi I by 6 into 1 over z raised to power 6 plus 1. Right, and then you can compute this value is 1 raised to power 6 e raised to power minus 5 pi I by 6. Right. Similarly, residue at e raised to power 3 pi I by 6 is equal to 1 over 6 pi I by 2 actually, and residue at e raised to power 5 pi I by 6 is equal to 1 over 6 e raised to power minus 25 pi I by 6. So I think all these calculations you can do. I am not doing that, but okay. So just take this expression and compute the limit in each of the cases. So so those 3 points I am able to find the residues. Now I can apply the formula that integration along C f of z dz is equal to sum of all these 3 values, right? Sum of the residues. So that means integration along C dz divided by z raised to power 6 plus 1 using Cauchy residue theorem is 2 pi I 1 over 6 times e raised to power minus 5 pi I by 6 plus 1 over 6 e raised to power minus 5 pi I by 2 plus 1 over 6 e raised to power minus 25 pi I by 6, and I can just sum them. You can simplify this value is 2 pi by 3, right? So essentially what we have, ये तो बहुत आसान था यहाँ तक, right? Key point अब आएगा. So basically integration along C dz over z raised to power 6 plus 1 is equal to 2 pi by 3. By applying Cauchy residue theorem, I am able to find this. What is C? C is a region starting from minus r to r and the semicircle, that gamma. Okay, the half semicircle. Okay. इस रीजन में हमने रेसिड्यू देखे कौन कौन, मतलब पॉइंट्स देखे कौन कौन से सिंगुलर पॉइंट्स हैं, उन पॉइंट्स पे हमने रेसिड्यू निकाल लिया, उन रेसिड्यूज को सम कर लिया. सो इंटीग्रेशन अलोंग सी एफ ऑफ जेड डी जेड इज सम ऑफ दोस रेसिड्यूज बाय काची रेसिड्यू थ्योरम. अभी क्या बाकी है, हमको तो रियल का वैल्यू निकालना था. नाउ व्हाट आई एम गोइंग टू डू, सी को ब्रेक करेंगे दो पॉइंट्स में, दो पार्ट्स में. माइनस आर टू आर नीचे वाला एक्सिस, एक्स एक्सिस का पोर्शन माइनस आर टू आर एंड दिस सेमी सर्किल. ठीक है, माइनस आर टू आर तो हमारा रियल में आ जाएगा बेसिकली, वाई तो जीरो कंपोनेंट होगा वहां पे, राइट? तो हमारा एक्चुअल फंक्शन आ जाएगा जिसकी वैल्यू निकालना है, प्लस बचेगा सेमी सर्किल का पार्ट, और वो जीरो होना चाहिए एक्चुअली, तभी हम वैल्यू निकाल पाएंगे. और वो जीरो कैसे होगा, यूजिंग योर फ्रेंड एप्सिलॉन, राइट? सो वो जीरो की तरफ दिखा दो, एन मीन्स यू आर डूइंग, समहाउ यू डू इट. सो एज द लिमिट हैपेंस, लेट मी शो यू. सो if I break it, minus r to r dx, sorry, minus r to r dx by x raised to power 6 plus 1 plus integration along gamma dz over z raised to power 6 plus 1 is equal to 2 pi by 3, right? So you need to show that this quantity here goes towards 0 as capital R approaches towards infinity. ये portion तो आपको क्या करना पड़ेगा, इसकी absolute value लेनी पड़ेगी. So integration along C f of z dz is less mod of, so mod of integration along C f of z dz is less than equal to capital M into L. प्रॉपर्टी है ना, वो बहुत यूजफुल इनइक्वालिटी है, बार बार यूज होती है, राइट? वो सब सम करके शो दैट कि एज r टेंड्स टुवर्ड्स इन्फिनिटी द होल एक्सप्रेशन गोज टुवर्ड्स जीरो, राइट? सो आई एम लीविंग दैट टू वेरीफाई दैट दिस गोज टू जीरो. गामा है तो गामा में यू नो दैट z विल बी व्हाट, r टाइम्स सीरीज फॉर i थीटा, वेयर थीटा लाइज बिटवीन दिस पॉइंट टू दिस पॉइंट, राइट? So then we are going to get minus infinity to plus infinity dx divided by x raised to power 6 plus 1 is equal to 2 pi by 3. Now since f of x is an even function, I can write down, this implies that 2 times 0 to infinity dx divided by x raised to power 6 plus 1 is equal to 2 pi by 3, right? And hence 0 to infinity dx divided by x raised to power 6 plus 1 is equal to pi by 3. You got the value. So the most tricky part, I mean rest of the things are simple, except you need to show that this portion goes towards 0. So I leave it as an easy exercise. It's not very difficult. Just take the absolute value. It will be less than equal to some quantity which will be function of capital R, and when you take capital R approaches towards infinity, the whole thing goes towards 0, right? So, okay, so that thing can be settled down, and so you can find easily. So this is a nice approach of finding the value of the integral, right? Now, not only this, you can also use second application. If you want to find integration along 0 to 2 pi, some function of sine theta cos theta, where g is a rational function of sine theta and cos theta. Okay, g is a rational function of sine theta cos theta. Then you can also use this. Then what we do? Substitute set z is equal to e raised for I theta. Then sine theta will be z minus z inverse divided by 2i, and cos theta will be z plus z inverse divided by 2. dz will be I times e raised for I theta d theta. So whenever we are given a function like this, dz. Whenever we are given a function like rational function between sine and cosine, I just do these substitutions, and then let us take an example. So here actually what we do, we compute integration along C f of z dz, where C is given by this kind of circular region. Okay, C circle is of radius 1, x axis, y axis. Okay, this is our C. So let us take an example. 0 to 2 pi d theta divided by 3 minus 2 cos theta plus sin theta, right? Okay, so put z is equal to e raised for I theta. Sin theta will be what? Z minus z inverse by 2i. Cos theta will be z plus z inverse by 2, and dz will be I times z into d theta. So basically I will replace this d theta, all these theta, in terms of z, right? So we get integration 0 to 2 pi d theta divided by 3 minus 2 cos theta plus sin theta is nothing but integration along C 2 times dz divided by 1 minus 2i times z square plus 6iz minus 1 minus 2i. Okay. Now this is a rational function in z. I can look at denominator is 0, so it will give you the singular points. So poles are nothing but z is equal to 2 minus I and 2 minus I by 5. So only this lies in circle of radius 1. So we can compute residue at z is equal to 2 minus I by 5, and that value turns out to be 1 over 2I. So integration along C, 2 times dz divided by 1 minus 2I z square plus 6iz minus 1 minus 2I will be 2 pi I sum of the residues, which is 1 over 2I, is equal to pi. Right. So this is the way of handling. So whenever there is a function in the form of sin theta cos theta and you want to evaluate from 0 to 2 pi, just substitute z equal to e raised to power I theta, convert everything into the z, and then you evaluate this where C is a circle of radius 1. Right. Look at which singularity is inside the C, this circle, compute the residue at that point, and 2 pi I times sum of the residues will give you the value. Right. So value of the integral is pi actually. Right. Now look at another case. So actually third case, when you want to integrate minus infinity to plus infinity f of x and times some multiplication function either cos mx or sin mx, where fx is a rational function. Okay, then we need to consider integration along C f of z e raised to power I times mz dz. We need to consider this integration along C f of z e raised to power I times mz dz. Why? Because now if I take y is equal to 0 in this expression, I am going to get something like that, right? So, and then here again C is that semicircular thing and so on and so forth. Let me explain to you what is that. So let us take an example so that you understand. We want to integrate 0 to infinity cos mx divided by x square plus 1 dx. So I want to show that this value is pi by 2 times e raised to power minus m. M is positive, right? But not by using reals, but by using complex numbers. So what I am going to do, I consider integration along C e raised to power I times mz divided by z square, integration along C e raised to power I times mz divided by z square plus 1 dz. Right. What is C? Again that from minus r to r and then semicircular region. Right. So what are the singularities? Z is equal to plus minus I, right? Z equal to plus minus I are the poles of order 1, simple pole, right? So I can compute residue. So which one will lie inside this circle, semicircle? You can see that Z is equal to I lies inside C. Minus I will go outside, so this lies inside C. So we can compute the residue at Z is equal to I. This turns out to be e raised to power minus m divided by 2I. So we have the formula, integration along C e raised to power I mz divided by z square plus 1 dz is 2 pi I sum of the residue, which will be e raised to power minus m divided by 2I, and this simplification gives us pi times e raised to power minus m. right? Now this can be broken into two parts, minus r to r e raised power I mx x raised power x square plus 1 dx plus integration along gamma e raised power I mz divided by z square plus 1 dz is equal to pi times e raised power minus m, right? So सब कुछ वैसे ही है जैसे माइनस इन्फिनिटी प्लस इन्फिनिटी केस में था. I need to show that this whole quantity goes towards 0 as r approaches towards infinity, right? Using absolute value and so on and so forth. So we are left with, again this is a even function actually, right? So I can break it into two times basically. So we will have minus infinity to plus infinity or minus r to r. Okay, yeah, that's I have written already, right? Yeah, minus r to r. So now this left hand side can be written as 2 times integration 0 to r cos mx divided by x square plus 1 dx, which is pi times e raised to power minus m. This implies that 0 to infinity as r tends towards infinity, cos mx divided by x square plus 1 dx is equal to pi times e raised to power minus m by 2. Right. So I think you got the enough idea. Okay. One more application is there. So I think we looked at 3 kind of integrals. This is one case. This is second case when the function of theta. Yeah, so this is d theta, sorry. I don't know why I have taken. And then the other one is like this, right? So if there is a, in the numerator sin mx cos mx, then I have to take e raised to power I mz. If that is not there, directly we can take in both of the, whenever the limit is from minus infinity to plus infinity, I have to take semicircular region minus r to r and then do the calculations, right? So now I will show you one example of, there are multiple ways you can find the sum of the series. I'll just do one example, that's all. I mean, there is no need to do a lot of things, but okay. And I am not going to even mention the result. By the way, what is this value? 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus dot dot dot. अगर इसको sum करें तो क्या आएगी value? Pi square by 6, right? कैसे prove कर सकते हैं? So one way of proving is use Riemann zeta function, right? Riemann zeta function जो देखा था ना? Riemann zeta function satisfy a relation on the argument z. उसमें हम z की वैल्यू रख दें, क्या रख दें? तो समेशन 1 ओवर n raised to power z इज देयर, राइट? z को 2 रख दें तो हमको सीरीज मिल जाएगी, राइट? तो बेसिकली by manipulating Riemann zeta function you can actually compute this value to be pi square by 6. एक मेथड तो हमने शायद किया है ये क्लास में कि नहीं? आई डोंट रिमेंबर, शायद पिछली बार कभी किया होगा. नॉर्मली आई डू इट. There is another way by looking at a function, look at the zeros, multiply and then do the simplification. That method was done by Euler actually. Euler's method is there. Now I am going to show you that series value is pi square by 6 using Cauchy residue theorem. Okay. Okay, so here we take a function f of z is equal to, I am not going to tell all the rules, but here I am showing what is the thing. There are rules given in the notes, you can look at it. What function you should take? Cot pi by z divided by z square, which is pi times cos pi z divided by z square sin pi z. So we take this function. When to take what function, there are rules, as I mentioned. I am not telling those rules, it is given in the notes, you can look at it, right? I am just showing you one example, right? When I want to sum this, I take this function where z is a complex number, right? Z square. Okay, then I expand this. This is nothing but 1 minus pi square z square divided by factorial 2 plus pi raised to power 4 z raised to power 4 divided by factorial 4 and so on, minus divided by z cube 1 minus pi square z square divided by factorial 3 plus pi raised to power 4 z raised to power 4 divided by factorial 5 and so on. I am just expanding the series, and finally after simplification this turns out to be 1 over z cube 1 minus pi square z square divided by factorial 1 over z cube 1 minus pi square z square divided by factorial 2 plus dot dot dot, other series will be 1 plus pi square z square by factorial 3 and so on, 1 over z cube 1 minus pi square z square by factorial 3 and so on, right? So basically we get a function like this. Now you know that z is equal to 0, this is our f of z, original f of z, z equal to 0 is a pole of order 3 here, right? Pole of order 3. So I can compute the residue. Residue will be at z is equal to 0 is, you can compute minus pi square by 3. So I consider integration along C, pi cot pi z divided by z square dz is equal to summation minus n is equal to minus n to minus 1 over n square plus summation n is equal to 1 to n 1 over n square. सब complicated लग रहा होगा, right? Minus pi square by 3. So this is nothing but 2 times summation n is equal to 1 to n 1 over n square minus pi square by 3. One can show that left hand side goes towards 0 as capital N approaches towards infinity. So we have 2 times summation n is equal to 1 to infinity 1 over n square is equal to pi square by 3, and hence summation n is equal to 1 to infinity 1 over n square is equal to pi square by 6. So essentially we have used here, of course this portion you have to show that it goes to 0 and so on and so forth. I am skipping a lot of things here, but I mean it's okay. Even if you don't do the series finding, it's okay, I mean, right? But there are ways you can find series, because there are some of the complicated functions you have to use for different kind of series, right? So I wanted to show that, yeah, there is a way to find, but that's all. I guess, okay. Yeah, so I think you are done with the complex. Okay, so should we continue or you want break? Break? Okay, then maybe 5 minutes break or something, right? Okay.